All right, so we're going to continue with the next speaker on a very, very important topic on bias in AI. So it turns out that a lot of the models that we use, these very, very complex AI models, can be really hard to interpret and they can have biases. So without further ado, please, Lijian, take the...
Can everyone see my screen?
Yes.
Okay. Oh, I cannot see the chat when it's...
I can let you know if there are questions.
Yes. Actually, a little bit to add on that. Actually, Conda would automatically deal with the dependency for you, but sometimes it mess things up because it wouldn't look at other dependencies. So maybe your current package dependency is working for other packages, but when you install by Conda, it will mess up the other dependency. But it's a good way to install TensorFlow. So I'm Lijian Liang. I was a first-year PhD student, and I will be a second-year PhD student at Syracuse High School. So in this section, I'm going to just introduce some very basic concepts about bias in AI. So in the previous sections, we learned about different machine learning models, such as like very simple ones like logistic regression, naive Bayes, very naive models. And today we have the opportunity to learn about more complicated deep learning based methods or models like CNN, RNN, STM, and some transformer based models. And even though how they work and how to actually create those models or how the inner decision-making processes might not be very intuitive, but I think the gist is with a bunch of labeled data, we can potentially develop predictive tools to better understand various very interesting topics like science, society, and the application of machine learning and artificial intelligence are truly amazing. So we don't need to understand how they actually work in order to be aware of the power of AI. And we probably have been using it all the time. Just think about the voice assistant that we use, Face ID or fingerprint sensor we use every time we unlock our cell phones. And the computer program that beats the world champion of Go chess is also amazing. And all those applications are powered by AI. And all of a sudden, all the people are talking about it and trying to apply it all the random things. And because it is truly amazing. So even though there are countless examples of AI that being awesome, it suffers some many flaws. One of the very relevant flaws is that some of those AI models might inherit human bias. So government have been using AI to make some very life-changing decisions. According to a report, some governments have been using facial recognition models to predict whether a person is going to commit a crime again in the future. So some very specific examples of the model predicting shows that those systems could often be biased. And in this very specific example, a white male with some criminal records could be predicted as someone who has very low risk of committing a crime in the future again. But very likely because the system is making a prediction using a face of a white man. But on the other hand, while predicting whether a black woman with very few criminal records, the system predicted that the person have very high risk to commit a crime again in the future. So this is another example. So Vision AI is a service provided by Google. It's basically an API service which could be adopted by many businesses, small businesses. And so it's powered by computer vision and deep learning. And is a perfect example of an application of machine learning and deep learning. And last year, human biases have been discovered in the image recognition model behind the service. So even though the company Google behind this service claims that the model has very good accuracy, it tends to make decisions with human bias. So in this very specific example, the model tends to predict that a hand with a darker tone is holding a gun when a hand with a lighter tone is holding a binocular. So this is an example happened a few years ago. So this is face recognition software, also powered by deep learning, was found to have a hard time figuring out whether a person of Asian descent has their eyes closed or not, for some reasons. So regardless of how powerful AI is when it actually works, having human biases embedding in those models could bring actual harm. Like for instance, quality of service harm will be done when a system does not work as well for one person as it does for another. So just think about the previous example of how the facial recognition software thinks a man has his eyes closed. I guess the model would work much better if that person is white. And allocation harm will be done when an AI-based system extends or withholds opportunities. And that kind of harm could be done usually when, for example, during a mortgage application or job application. So people in the industry have tried to fight against algorithmic bias brought by deep learning and AI. So in response to the Black Lives Matter movement last year, like large tech companies started to restrict the use of AI that might contain bias against minorities. So just to list a few examples, on June last year, IBM announced that the company would exit the general purpose face recognition businesses. And Amazon had announced that all the police are forbidden to use their facial recognition software service. The basic building block of AI and deep learning and machine learning models are actually mathematics and code, according to what you have learned for the past few days. But when we first think of all of those things, we usually regard them as like code and rational and very objective. So it could be kind of a surprise that there are human bias hidden in code equations and computer programs. But to explain why machine learning and AI models might be biased, we need to go back to the step we take to build those models. To build a machine learning models with predictive power, we will first need to have a human labeled dataset for supervised learning. And what we try to do is to minimize the prediction error by constantly update the coefficient in the model. And at the end of the day, we'll eventually get a model that knows the pattern, learns the pattern in the training dataset very well. And by evaluating the model performance on validation data, we test how well the model might work actually in the real world. Then if it has a good performance of the validation split, we'll use it in multiple real world applications. But there are a few steps before and after the model training steps. So first of all, for supervised learning tasks, it's impossible to train a model without training data or human annotated datasets. Those data are painstakingly collected and annotated by humans. And after training the model, before and during the model application process, we need to interpret those models to get more knowledge about the task. So a proper interpretation could be, for example, like checking the feature importance or comparing the size of the coefficient for much simpler models like logistic regression or random forest. And so with proper interpretation, we'll have a better understanding of the problem itself or the research questions. And based on that better understanding of our research question, we will change our ways to collect, annotate, and curate datasets. But in this whole process, different kind of human biases could appear. So during the annotation process, annotators who have painstakingly labeled data for model training could come from very different backgrounds. And because we're human, we are all biased in our own different ways. So they might have, those annotators, they might have different gender, ethnicity. Each of them have their different views about how the world works. And so it is possible that the dataset could inherit annotator biases in the creation process. And the final product of the annotation process could be biased labels. And for the data collection process, researchers might take a random sample for model training. But sometimes the model selection process could also have some human biases. Like, for example, I think, I'm not sure Lucy or who have mentioned that in the dataset, because of language barriers, they don't have much of the researchers or publications outside of the US or European. So in that case, the scientists outside of America or other English-speaking countries will be missed out from the dataset and thus being underrepresented. When we want to train a model, we usually want the training dataset to be a random sample or a vivid representation of the real population. But due to selection bias, the dataset might not be ideal and could inherit human bias. And dataset itself might also infer human bias aside from the selection bias or annotator bias. For example, there are a few language models that are based on word co-occurrence, such as word embeddings. And the co-occurrence of words in historical literature might have some human biases. For example, historically, there are more female nurses than male nurses. For example, the model might tend to believe a nurse is more likely to be a woman than a man. So in a study we did in 2020, by using a method from psychophysics called two alternative voice choice, we found that word representations models might have gender bias for occupations. So because in the historical literature and how word co-occurrence works, the word representation tends to believe that some occupations like hairdressers or teachers are more likely to be female, while occupation like electricians, technicians are more likely to be men. So at the end of the day, after the whole training session, we will have a model that performs very well on the validation split. So at this point, we assume that the model already have a very good performance on the real world. So in order to better understand the prediction task, we usually try to interpret the model. But in that process, there will be confirmation bias, overgeneralization, and correlation fallacy. When researchers or engineers are interpreting the model, the process might be influenced by their own belief or pre-existing hypothesis. And on top of that, there might not be enough information for researchers to draw any conclusions, maybe because they're using a different sets of features that fail to capture what is actually going on for the prediction task. In that case, if they can't come to a conclusion based on partial interpretation from a model, they might also come to a conclusion that is partially correct. So even though, human biases are present in multiple stages in the model building iteration. So in the loop, human biases will accumulate if we ignore the phenomenon. But even though we might be aware of the biases hidden in machine learning and deep learning models, it is still challenging for us to understand how exactly machine learning models make a biased decision. So in the previous section, we have talked about less complicated models like logistic regression. So it is relatively easy to interpret because each feature corresponds to one coefficient. So by simply naively comparing the size of the coefficients, we know which feature is more important. But when we look at multi-layer perceptron, it's basically several sigmoid functions stacked together. So at this point, it's very hard to tell which coefficient correspond to which feature. So it's quite challenging for us to tell which feature is more important in this classification task. So this is a graph showing the relationship between accuracy and interpretability that I think Daniel showed a few days ago. So typically more complex models could fit a more complicated curve. So they typically have better performance, but causing the interpretability. Well, the purpose of this section is definitely not to scare you off so that you never use those machine learning models anymore, given that Daniel and Han have just painstakingly introduced how to use machine learning and deep learning models. But given all the setbacks, we cannot ignore that the fact that all those AI applications have the potential to make our life easier. With artificial intelligence and deep learning, we can make better decisions, better discoveries, and it helps us better understand the world. And so that we should not throw away the entire apple just because of the core. So, but there are a handful of procedures we should do to mitigate algorithmic bias from AI or machine learning models. We should be mindful of fairness in each step of model building. So in the data preparation step, we should understand skewness and correlations in our data. We should learn whether all subsets of our data are equally represented. For example, in a dataset for facial recognition application, is the number of white faces equal to the number of Asian faces? We should acknowledge the imbalance in our dataset and do proper adjustment. For some tasks, we should remove data points that include stereotyping, sexism, and racism. And if certain groups in the dataset are underrepresented, we should seek more data for those subgroups from different sources. And in model training step, we should do proper cross-validation, always cross-validate, as Daniel might said, so that the model we train has better generalization power, in the sense that it is more likely to do a good job in the real world. And we should also define a held-out test set for high use cases. Like, for example, define a list of test sets with only African-American researchers and see if the prediction of future success also makes any sense. We should also be mindful of what feature we choose for model building. We should identify and remove sensitive information that is irrelevant to the prediction task. And one example of mitigating human bias in the classifier training step is using multitask adversarial training. So in this example, we have, for example, this is a multi-layer perceptron. This is black because this is a black box that we have no idea what it is doing. So on top of training a target, so this is the true task that we are trying to solve, say future success of researchers. On top of that, we also add another classification layer to predict the gender, race, etc. of that researcher. But instead of minimizing the cost here, we maximize the cost. So that in a sense, that the classifier one implicitly predict the gender or race for that data point. So no gender or racial bias will be introduced in this process. So after we have a model that we assume might work great in the real world, we need to have like proper metrics to evaluate whether a model is fair. So this is a confusion matrix that we showed earlier on Tuesday. So based on the confusion matrix, we have like several ways to measure how good a model is, like for example, F1 and recall and precision. And here I will speak more detail about recall and precision. So in some cases, we want to minimize the false negative in the prediction task in the validation split. For example, if we want to predict whether a paper should be retracted or whether a journal is predatory based on a classification model, we want to make sure that we don't make mistakes or we might get sued. On the other hand, sometimes we want to minimize the false positive cases. For example, for a spam detection model, the last thing we want is that good emails being classified as spam and it end up in your trash can. So here is two metrics we use to make sure the performance across subgroups works equally well. And here is two tools, one developed by IBM and another developed by Google, not sponsored, and they provide very useful method for you to interpret complicated models and visualize your data set so that you understand the imbalance in your data set. And that's the end of my talk. Thank you. And so I have two examples or activities that you could try. So one is the case that we showed earlier, showing or detecting the bias in occupation towards occupation in web embeddings. So by running this script, actually I have a module in the last directory where you can import methods that do the 2AFC experiment. And by running this function, we can import a 100-dimensional graph pre-trained word vector. And by walking through this notebook, we can essentially recreate the experiment that I just shown earlier in the slides. And there's another one that talks about how to use Hugging Face and how to use transfer learning and apply it in your classification task. So here, I'm using fine-tuned BERT model that is called Spectre, which is actually developed by LNAI. So it is fine-tuned based on BERT, but it also add tasks so that the model is mindful of the citation. So it does a pretty good job in terms of creating unsupervised representation of sentences in academia. So because of the limitation of our hardware, I have pre-computed, even though I have a demonstration on how you can use the Spectre to generate a sentence or document vector, I have pre-computed, I can recall 40,000 sentences from the citation worthiness data set. So you can use the data set to train logistic regression. Yeah, that's it. Thank you.